because of the limits, like fears, are often just illusion. So I think that's also very important to say. Also, another example we have in nature, for instance, you have here the Bengal tiger, which needs an average of 10 attempts if he wants to hunt a deer. 10 attempts. So the tiger doesn't know if it will be the first, the second, or even the 10th attempt in which he will be able to hunt the deer, but every time he puts a big efforts to do that. So that's something very important. Also, and this is from me, I don't think that the tiger complains or get frustrated or thinks why me or something like that. He's just doing his best every time. Yeah. So in that sense, I know that it's not only important to be the pioneer on something that you believe. So it's very important that what you develop, it's something you believe from the beginning. Otherwise, it makes no sense. If you just work because of the success, it's not going to happen. So it's very important to be aligned. What you say, what you think, what you feel has to be in only one line. And that's very important. I also very proud because not only myself, but also my first PhD student, it's also now awarded as a highly cited researcher. So also for me, it's very important that my PhD students can also be leaders. And that's also something very, very important that sometimes we forget. And we have created right now a center. The center started last year, even though that the Microgrid research program we started 10 years ago. And I will say that right now we are around 40 to 50 people working together in different aspects of microgrids. And I would like also to thank them. I know that some of them are also connected here, though, so thank you very much for that. And the other important thing is let's say to have a vision that it's, let's say, after you. So you become less and less important, and let's say that the motivation who drives you is more important. So I will say that right now we have, yes, we have a lot of fancy things, but we can see that still 2.7 billion people in the world don't have access to electricity, and this is a problem. And at the same time, we need to accomplish a lot of targets to make possible the transition, like we have here in Denmark, to go for 100% renewable energy. And the other important thing is also regarding what is the concept that I have been developed. It's not from the beginning that I wanted to develop microgrids, because at the beginning I was just working for a company to develop UPS systems, and they wanted to put as much as possible in parallel. And they liked the idea of avoiding communication between them, even though I am a communication engineer, which is kind of funny, a communication engineer trying to avoid communications, right? So after some years of working on this area, I realized that these control concepts could be expanded on something that was very new at that time, called microgrid. You have to think that all those concepts I started to develop around 2000, and at that time it was not still the microgrids developed at all, right? So I will say that also it's something that is coming, and you don't know why, but you have, let's say, the intuition that you go on that direction, on something that you really believe. And I will say that right now one of the main topics is also going to what we call also microgrid clusters, which is not only to have a number of converters connected in parallel and to collaborate, but also a number of microgrids, so that we can reach unprecedented levels of scalability, let's say expandability, efficiency, and resiliency. So this was a little bit my vision that moved you, let's say, towards this idea, no? To have a number of microgrids that could be really integrated also in real applications. Yeah. Also, a little bit talking about what we call also ideas. My idea always was to go to non-populated areas. So let's say that if at that time it was not almost nobody working on droop control. I was really attracted to that. So if you see an area which is very, very populated, just I will tell you, don't go ahead with that. Just try to go on something that you believe that is your vision. Yeah. So it was more or less in 2000 when we start. You can see here the research works, almost nothing in microgrids at that time. And it was more or less after my PhD, I present the first paper in 2004. It was really a conference in 2003 that I just went there for relaxing after the PhD was complete. And then I converted to a transactions paper. This transactions on power electronics paper was criticized a lot from the reviewers. They said that this was better maybe for a journal on power systems. Yeah, at that moment, I present by the first time an improvement on the droop control and presenting the first ideas on virtual impedance. Yeah, so you have to imagine that this journal right now, it's one of my, let's say, highest cited ones. And so I fully understand when people send a good paper to a journal and then they got like very negative opinions from reviewers. So you have to understand that you have to push for that. And this is what happened indeed. And it had very good, let's say, acceptance. Indeed, this idea came from the solution of a problem that the company gave to me. So the company really wants to have modular UPS systems. They wanted to get rid also about output inductances. And then thanks to this idea, we could come with that. It was really 3 years of work. So you have to imagine also that how it's hard to really enter in a new area. Yeah. After this and working many years to avoid communications, then I start to add communications also inside microgrids. Yeah. So it was also because another company, we were working also many years, and right now we are still collaborating. They are not under the same name, but they just changed the brand. And we have to solve another problem, which was the transition between grid-connected microgrids to islanded mode. And at that time, I had to build, let's say, a full communication system. So I kind of go back to my origin of communication engineer, let's say. It was a while later that I developed the idea of having microgrid clusters in a very early paper, which is right now also highly cited. And then we start to, let's say, with this kind of microgrid clusters to reconsider how it should be, let's say, the smart grid. And then we enter in a period in which our center, let's say, started last year. And I try to expand all these ideas to many other concepts. I will share with all of you now. So you can see also how we have a lot of restrictions when we talk about microgrids, but then when we go to clusterization, we can really go and to redefine smart grids from the microgrid perspective. And I will say that this is thanks to a lot of transdisciplinary research areas like telecom, like people like myself, or other colleagues that work on computer science or artificial intelligence, and even biomimetics. So I will say that this is bringing a lot of new knowledge, like cyber physical systems, complex systems, and resilience microgrids. So going to a more, let's say, advanced area. And another interesting thing is that we have some use cases, for instance, how we can use prosumer microgrids also, how those microgrids can be implemented in homes and using many of these electronic loads and generators that we can have. But also it's still very important to think about rural electrification. Let's say in some areas, these, I think it's a picture from the Tibet, sorry, in that case it's from Nepal, in which some of these microgrids also are being reconsidered to be also going to DC, or also thinking on resiliency against natural disasters. Yeah, so that's why also we developed microgrid facilities in our university that we are able to connect a number of microgrid systems in parallel. So it's really to test single microgrids, but also multi-microgrid clusters. And I will say that this is unique. So you can see some of the use cases that we are working here. It's not only rural electrification, marine systems, space systems, also more digitalization inside. So you can see here our different research frameworks that we have in our Center for Research of Microgrids, going from microgrid clusters, as I showed before, the vision, microgrids in shipboards, in the ports also, in the space, and then here is more working on what we call also digital twins and digitalization. So in our laboratories, we have electronic systems, as you can see here, connected to a digital signal processors that can be directly programmed from MATLAB Simulink. And we wanted to do this because we suffer many years trying to program DSP systems. And we know that many of the students and also the researchers in the world are working with MATLAB Simulink. So we have an interface that if you use MATLAB, for instance, we can try to test your algorithms. We thought that also having a number of power electronics converters in parallel could be good for us to test also microgrids. So if you have ideas also, you are very welcome to contact us and we can remotely collaborate and test your ideas and algorithms. Yeah. And going beyond also ideas, we have developed also what we call also a microgrid living labs. So in that case, we have erected small wind turbines and also photovoltaic systems. And we have also a number of appliances as well. So we have appliances here that, let's say, are connected through Zigbee. Yeah, there are some other pictures also of our, let's say, facilities. We have the control room, we have the office, the living room, the kitchen, and now you will see also some pictures here about all these spaces in which we have sensors also, and then the control room in which we have also the typical smart meter that we have here in Denmark, and then a number also of connection, especially Zigbee connection with all our appliances. Here you have the detail of the smart meter. It's exactly the one that we have at home. And then we have here a number of plugins. During this month, also, we're going to have an installation of a fuel cell. And this has been also announced right now. So if you have interest also about the fuel cells, is a cooperation with another company here in Aalborg called Ser Energy. And the battery system is from another company from Germany, Sonnen Battery, in which we are also collaborating in another project. So let's say that we have a lot of industrial collaboration. And then we have also the Velco, which they are here in the city of Aarhus in Denmark. And they provide you plugs that are able to connect by Zigbee through the main, let's say, control system of your house. And also we have plugs from Fujitsu, these ones on blue, which are DC plugs. So also we have the possibility of testing DC ideas. Here you can see also the 3-phase and also the blue plug for DC distribution. That's very nice. And we combine also these ideas also with those kind of, let's say, microgrids inside the lab. Yeah. Also, together with the Delco, this company, we are developing an IoT application for this kind of houses together with Zigbee and also MBus. Right? Here you can see some of the components. And then we have finally an architecture by using also database systems. So you can imagine that we have a team on computer science also working on that. Right? And then we are also able to develop demand response algorithms. So this is something very, very nice to develop, but in, let's say, in the house level. We are not making simulations in that case. We are really using the house as a demonstration lab, right? And we get all the information, let's say, from the smart meter and each of these smart plugs about air quality, and also if someone enter, what happened with the temperature of each room, active, reactive powers, and so on and so forth, right? So we have a full monitor system. We are also able to make load monitoring, and in that sense, we are able to, by using intrusive load monitoring. So that means using those kind of smart plugs, we can extract the information, but also we can use non-intrusive load monitoring, because we understand that not everyone at home, they can use, let's say, intrusive plugs. They have a general smart meter. Also important thing is that when people think about smart meters, they think that it's only electricity, but electricity is just a small part. We have also smart meters for water, for gas, and district heating. So all these things are, let's say, interconnected with MBUS. And also we have been developed some work with Chemstru, which is one of our partners in the side of smart metering. And in that sense, we also test the smart meters also with, let's say, a concentrator. I think it's very nice because just with an optic eye and a USB cable at home, you can get the information of the smart metering. In that case, you can see also how are the three phases, if you have some imbalance, for instance, and if you have some under voltage or over voltage. This is more or less how it looks, let's say, our setup. We have also floor heating system, yeah. But you know, after some years researching microgrids, I decided finally also to test all these things on my own. So I feel really disconnected, and it was in some point that I had to move from one house in the city center and have my own house outside. So I needed a car, and I didn't thought two times. I just go for an electric vehicle one. And then I install an electric vehicle charging station. And at the same time, I also install a photovoltaic system, right? So this is in the front of my house, and then this is in the entrance. So you can see that right now also the government is reducing more and more the feed-in tariffs for solar. So that's why that I try to use as much as possible the solar panels. Yeah. So it was a little bit like a dog taking your own pills. And everybody knows that one of my favorite doctors is Dr. House. And one of the favorite statements also is, if you really want to do something, you will find a way. Otherwise, you always will find the excuse, right? So it's a little bit also talking about motivation, no? And motivation also is connected with artificial intelligence. So everyone is right now talking about artificial intelligence for those systems. But my question is, do we really know how work our brains? And recently we know that neuroscience discovered that we have neurons not only in the brain, but also in the heart and in the gut. And this is very important. And I will say that it's very well connected with ideas like chakras. Right? There is also that sometimes we wonder, we say how much we use our brains. In the past, people said maybe 5%, maybe 10%. Right now, we know that we use 100% of the brain. However, due to limitations of oxygen and glucose, we can only use 2% at the same time. But it's basically blinking all the areas. However, we normally use similar neural network paths, and that's why it's so difficult that we change when we want to do it. And at the same time, the same brain also have like 3 levels of, let's say, of control. We have the reptilian brain, which is like acting, like action reaction, no? Limbic brain, more connected to emotions, and the neocortex, which is really the rational brain, right? So you can see also here the number of years, and now you understand why major part of our decisions are based on emotions. You cannot compare 100,000 years to 200 million years. So that's why many times we take a decision based on emotions, and then the rational part, the neocortex, comes with the justification. Yeah, very funny, let's say, 3-level control system that we have in our brains. But also what is very interesting here is to see why sometimes a positive stress can be even good. So we have, if this is for a very old, let's say, study from Professor Yerkes and Dodson, and they discovered that with moderate levels of stress, you can reach, you can generate neurotransmitters, which are also some of them generated by the heart. and you generate dopamine, which give you motivation and also, let's say, aims of learning, while noradrenaline also activates the attention. Yeah. However, if the stress is really increasing a lot, then we pass to what we call also de-stress, and then we can go to the burnout phenomena. So also we have to regulate about that. Another important thing, it has been discovered very recently, the same areas of the brain that are activated when you have fear are the same that are activated when you trust. So you cannot trust and have fear at the same time because you use the same areas. And I would say that, that's very important, no? To manage yourself. And then also, we know right now which are the areas that we use for logic and emotional empathy. And another important thing is also how we have been discovered recently that a lot of communications are coming from the heart to the brain and not so much from the brain to the heart. So now the question is, who is the boss here, right? And that's not strange, especially with some studies coming from HerzMath Institute in Germany, in which they are measuring the heart rate. And you can see when you are in incoherence, so feeling frustration, for instance, how this heart rate, it's having these high frequency components, while when you are in coherence, you have basically a sinusoidal signal. So it's not bad that the heart rate is changing. It's good because finally what you want is to maintain constant is the blood pressure. So you achieve this by changing it. However, the way that you change, it's showing us what is your level of coherence between your brain and the heart. No? I will say that this is amazing. Also, a lot of studies right now, the scientists are measuring also that the electromagnetic field coming from the heart is 5,000 times bigger than from the brain and can be measured in even farther than 3 meters with, let's say, our instruments. And that's very nice. It has been also done a lot of studies seeing how also those hearts can interact each other. For instance, the heart of a boy with a dog, and that's why also a lot of studies has been done on how having an animal can help people who live alone, or how also having a partnership or a family, all those hearts are finally synchronized once they are close to each other. Moving a little bit farther about microgrids, let's say that we can see that in the market there's a lot of photovoltaic systems that we can, for instance, buy, like having grid connected systems or islanded systems. And in that past, we had like two opposite philosophies. One fixing the current, let's say, and the other trying to fix the voltage and frequency. So basically it was two opposite philosophies, and it was not the possibility to interact with the grid. Right now we have a lot of, let's say, gadgets in the market, like for instance, SMA, and you can see how they are performing also, for instance, frequency regulation. So that means that our photovoltaic inverters, if the frequency goes up to a certain level, you start reducing the power. And this way they are also participating on the frequency of the power system. This was also a patent from SMA, in which they use kind of a variant from the droop control. I can demonstrate if you want that is nothing beyond what is in the state of the art, but maybe the way of implementing it's how they got the patent. But finally, the idea is kind of the same, right? You can see other companies like Fronius also coming with similar ideas. In that case, it's Fronius connected to a Victron. So Fronius basically with, let's say, inverters connected to the grid, and the Victron connected to a battery system. That is one way, let's say. And the other is to try to build different systems in which you could have some of them injecting maximum power, like solar systems, and the other trying to maintain voltage and frequency. And then trying to have an interaction between, let's say, them. So that means that when the state of charge goes higher than certain level, let's say for instance 90%, then the frequency of the system starts to increase, so that the photovoltaic system reduce the power also, and they find, let's say, a stable point of operation. So right now it's how microgrids are operating right now, and you can find all these elements in the market. So it's nothing so strange right now, right? So here you can see a little bit more about the explanation of that. In that sense, we developed some years ago a collaboration with China and the University of Tsinghua, and together with the Ministry of Science and Technology of China, Kejipu, and we came with this demonstration, and you can see here that we have been used for each of the steps IEC standards. So in that case, it was European standards applied in many different concepts. One of them, I think it's very important, is to use, for instance, IEC standard for energy management systems, because still there are some people that don't know that when you have to develop an energy management system, there is already standard for that, and I think that we can use, and that's very interesting. Collaboration also was with Huawei, because was providing the inverters, and right now we are also closing another project with them. And this is how it looked like, the photographs. So it was photovoltaic systems in the roof, and then a couple of wind turbines we erected close to that system, and then lead acid batteries. So it was a complete microgrid, able to connect and disconnect from the main grid. Another project we did also, this was in cooperation with the Chinese Academy of Science, was to integrate hydropower systems with microgrids. And it was a process, let's say, of modeling the systems. And then you can see that we talk about megawatts. So it was a 2 megawatt solar plus battery system to work in parallel together to 2 hydraulic power plants. And basically here we were working on stabilized frequency and voltage. Yeah. So then we made a scale down model after testing it, and we could extract some experiments, let's say, with this scale down model. And you can see here also how we were, let's say, playing with the frequency regulation, and also deciding how much power is coming from the hydropower, how much power is also coming from the microgrid system. In that sense, it was very good, let's say, experience. And if we think about microgrid configuration, also you can imagine that there's a lot of power electronics elements in, but also you have to consider that sometimes those microgrid systems are also connected to the medium voltage. So, and sometimes also you could have, for instance, connections to gas turbines as well. This is one example from Japan. And one of the important things is also to define the load. So you should have some loads that could be adjustable, shadable, or sensitive. Yeah, this is a figure from Wisconsin Madison University. And then some other examples of microgrids you can find also in Jeju Island in Korea, yeah, and also in Japan. So in which they have been combined also gas engines with photovoltaic systems and small wind turbines. And I will say that also in Japan they have one of the more famous microgrid system, which is this in Sentai, and Sentai is very close to Fukushima. So you had here like photovoltaic systems together with a fuel cell, and also it was some gas engines, a couple of gas engines. So when it was the disaster, let's say in Fukushima area, I will show you a little bit more. These are just some figures about, photographs about the disaster. This microgrid was working 3 days. I landed without being connected to the grid. One full day, the first day, let's say, just working photovoltaic system with batteries, and the second and third day, the gas engines were reactivated. Yeah. So thanks to that, people could also talk with the family, because it was linked to the telephone systems. And also people could, let's say, go to the hospital because it was also connected to a hospital. Yeah. Another thing is about operation, so I will not extend so much. We know that a microgrid can work, let's say, connected to the grid, but also can work, let's say, isolated. And then we have, sometimes this is plane, but sometimes this is non-plane, and this means that suddenly we have a blackout. And you can see also here some other example of islanded microgrid systems, for instance, here in China. And you can see how, let's say, photovoltaic systems can work together with battery systems. In that case was also, let's say, a diesel engine there, right, to supporting. Talking about control, everything is fine when you have only one of your, let's say, units supporting voltage and frequency and all the other trying to inject power. But what happens when you have a number of, let's say, voltage source, or what we call also grid forming converters? Then we have to, let's say, add some drupes, and we can follow what we call also the inertia principle. So the inertia principle means that when the frequency is changing, I will also change my power. And this is something that you can do with, let's say, synchronous generators, but once you have power electronics converters, you need storage if you want to achieve that. And that is the point, no? So I always like to find this, show this example because it's very nice. A number of metronomes, all of them, let's say, desynchronize between them inside, let's say, a table which is floating, and after some time, they get synchronized, right? So this is the same idea that we have once we go into drupe control. So once the power starts to increase, we just reduce the frequency. This is something that synchronous generators do normally, but not power electronic systems. That's why we have to implement those kind of drupes inside a digital signal processor. And this makes us that if we have a number of these converters connected to the grid, frequency will be stable. However, if suddenly they are disconnected from the main grid, they need to pass, let's say, in island, and then the frequency will be dependent on the power. So that's why, taking the main idea from big power systems, I try to implement these three levels of control, of hierarchy of control, saying that here the primary control is going to be like the virtual inertia systems, like the drupe controllers that we developed for many years. And then a secondary control will try to restore all these frequency and voltage deviations. And finally, a tertiary control, which is the energy management system, will just adjust the coefficients, for instance, of our drupe controllers in order to get, let's say, an optimization of the operation of the system. This was the main idea. I will say that big power systems are doing this, so this idea is not new, but we try to adapt this idea to small systems, and many things change. This is from big power systems, so you can see how the inertia is really big. But however, in our case, we had to take care not only on frequency, but also in voltage, because in a microgrid, voltage many times is very well coupled with active power because of the resistive nature of the lines. So we could do many things also in a decentralized way, let's say, having a number of, let's say, algorithms working on different modules. And then by means of communications, we could control with central controllers. This is what we call central control. Or the other idea is to have totally distributed algorithms that they can work autonomously and they could talk each other, right? There is not a final solution for this. So sometimes you have to put algorithms centralized. Some other times you have to put algorithms in a decentralized way. And there is not a unique solution. And I will say that this is why this is very nice, because combination of both solutions give you a very good, let's say, performances. And this is what we experience also with many collaboration with industry in that sense. With the same idea of hierarchical control, we can build also to connect a number of microgrid clusters. So that means that this hierarchy of control, primary, secondary, tertiary, we could repeat if we need to connect a new microgrid. so building another secondary and tertiary control for the microgrid cluster. And so that means that while I'm enlarging my grid, just adding microgrids, I don't have to rebuild the control and the communication system. I just have to build things on the top of that, right? And I will say that this is very nice, the idea to go on this direction. Yeah. Some microgrids we can find also are, for instance, more and more in aircraft. So we have more electric aircrafts like this one from Boeing 787. It's not full electric, but some parts are going to electric. And this means that they have some fans acting as generators, let's say. And then you can see that this is a combination between an AC and a DC microgrid. So I will say that that's really cool. And another place in which also microgrids are coming is in ships. So you can see here an example. In that case, it's a DC microgrid for a ship. A number of diesel generators connected to rectifiers and then going again connected to the motors. Yeah, this is just one example from Siemens. We have also ABB concepts, for instance, going from AC to DC as well, but in that case they increase the voltage in order to put the converters very close to the propulsion loads. I will say that this concept is also very nice, and they are, let's say, applying for vessels of, let's say, less than 20 megawatt, right? So we can see also some of these vessels that they were working on AC, some of them are shifting to DC, because you can see in this graph also that the diesel generator can operate on a better point for certain, let's say, rotational speed at certain power. That means that the frequency of this bus is fixing, which is our operation mode. However, if we work on DC, this operation mode can change, so we can have more or less flat response. Yeah? This has been also obtained in some other vessels, like platform support vessels, especially right now that a lot of offshore is coming, and offshore wind is coming. This means that we need ships transporting people, energy, goods, etc. And this is a study that has been done in Singapore, trying to see how these vessels, when you shift from AC to DC, you can gain, let's say, efficiency. And you can see it very clear because, as I explained before, if you go on DC, the rotational speed of those generators is independent from how is the system, because it's basically on DC through a rectification. While if you work on AC, you will have just one operation, let's say, point that has high efficiency, but all the others will be out of the efficiency, better efficiency, let's say. You can see also some other, in that case, is an offshore supply vessel, and that comes from Norway, that Viking Lady. It's also a combination of fuel cell together with conventional generators. So in the fuel cell, since it's working on DC, it's nice because it becomes a DC microgrid system working in 1000 volt to support the already existing equipment. Yeah? You can see here the picture of the fuel cell, so it's not something small. But I will say that right now fuel cells are coming back. Yeah, that's why also we are installing in our laboratory also a fuel cell, and we want to also study how this will impact in let's say, microgrids like in ships. This is another project that we did and has been published in IEEE Spectrum. But the study was to, let's say, retrofit an existing ferry in Taiwan. And in that case, we just move out all, let's say, the old stuff. We put power electronics in, you know, the company called Vicedo right now becomes one part of Danfoss, one of the companies here in Denmark. And here is how it looks like. So we had a couple of diesel generators connected to a power electronics converter, generating a DC microgrid system, and then connected to a battery system. Yeah. So this way we could work a hybrid, let's say. Right now we are working on going towards full electric ferry. This was, by the way, the first hybrid ferry in Asia. So we are very happy about that. You can see here some pictures, the electric motors, the battery systems also. And we are right now looking for more ferries also. And another important thing is because not only we need more electric ferries or electric ships or hybrid ships, also here what you can see is that we need also to support ships also with electricity, and this is not obvious. So many ships comes, they are maybe conventional, but they need electricity for instance, freezers or other appliances. And the first thing that they do once arrive at port is to start diesel generators. So we tell them to stop, let's say, the pollution and to connect to a docking station in port. And as you can imagine, this creates a lot of possibilities, like having, for instance, DC microgrid systems to support through power converters, depending on if it's 50 or 60 hertz, the needed frequency for the power on that ship. And as you can imagine, this is, let's say, challenging the electrical infrastructure of the ports. Also, what we are doing is to look at the cranes. There's still a lot of cranes depending on diesel generators. And it's very interesting here to see that once the crane is pushing up the container, we need to inject energy, but once we are falling down the container, this motor becomes a generator. So we could regenerate the power, putting it back to our port power system or storaging, and this gives us between 40 and 50% of energy recovery according to different independent studies. So I will say that this is also something very exciting that is coming. Once we finish with the Earth, also space is also becoming more and more important. We have here in Aalborg an important company called GOM Space, and we are collaborating with them to develop DC microgrid systems that are going in nanosatellites. So they are basically solar panel systems together with power electronics and batteries and so on. But here the challenge is that when we have one of these satellites, we could have, for instance, problems like solar storms or cosmic radiations that could generate latch up problems. So that means that microprocessors should not command the power electronic systems. They have their own analog controllers. And then the microprocessors, they work as supervisors, let's say. There's a lot of challenge here also because there's a lot of pulsating loads. So it's something very exciting. And finally, I want to show you another example in which also looking at this main driver about the space, we have been seeing that also in the space we need what we call also closed ecosystems. This is a project we are doing together with the University Autónoma of Barcelona and the European Space Agency. And those ecosystems, there are some of them around the world, but the most, let's say, advanced right now is this one in Barcelona with the European Space Agency. And the idea is to support the life, the oxygen of the crew members, especially when you have to think about the International Space Platform, or if you are in a future Moon or Mars station, then you need to create the oxygen for them. And you have to think that this is like a closed ecological system. So you have several compartments, several bacteria also, and the cabin crew members has to pee, has to poo, and all this becomes nitrates, and these nitrates then we have to combine sometimes with oxygen, combining, let's say, minerals with oxygen, we obtain nitrates, and then we can create also, by using these nitrates and giving it to the plants, like microalgae, we can also generate more food, and we can generate more oxygen, let's say, coming from the CO2, and by using some plants, we can also take out the CO2 and generate more oxygen. So I will say that this is really a very complex closed loop system. You have to think that each of these compartments has more than 50 state variables. So it's not exactly like a microgrid, it's much more complex. But we thought that really we could solve the problem because we have like a closed loop system in which we have to set oxygen for the cabin crew with a very, let's say, narrow objectives, let's say around 20%. And we made, let's say, a parallelism between the closed ecological system and the microgrids, in which photosynthesis had a correlation with photovoltaics, oxygen storage with energy storage, and microbial fuel cells with hydrogen fuel cells. So thanks to this idea, we start to develop also here a hierarchical control. And in that case, we developed the digital twin for them. And we developed also a hierarchical control structure for these kind of elements. It didn't exist, the hierarchical control applied for closed ecological systems. So we use the primary control that is used for voltage and current regulation, just for mass flow regulation. Then the secondary control, which is voltage frequency restoration, we use as corrective actions like prescription or flow dispatch. And the tertiary control, which is for economic and, let's say, optimization in the operation of microgrid, we use in that case for design the long-term optimum operation points for the entire closed ecological system. So we successfully finished that, and we are really proud of that. Right now it's going to appear next in the magazine of industrial electronics of the IEEE. So if you have the interest, I can share with you the draft. So thanks a lot for the attention. And I want to finish with awards from Pythagoras. He said it is required to find the infinitely big inside what's infinitely small to feel the presence of God. Thank you very much.
Thank you so much. So we do have a lot of questions, and I'll start, from one question on the top. So can you please comment about cybersecurity aspect of IoT in this microgrid, the one you talked about?
Yes, well, about cybersecurity, also we are, let's say, working on that. And right now we have a PhD student looking at that. I think he's also connected here. So we look on that from the perspective that we, let's say, accept that the intruder already entered in the system, and we observe how some variables are changing in order to take actions. People in computer science are also trying to avoid, let's say, that the intruder enter in the system. So this is, let's say, two ways of working. Mm-hmm. So let's say that they work, let's say, fighting against the entrance of the intruder. And what we do is we consider that the intruder is already there, and we see how the system reacts in order to detect that we have some malicious attack there. So I will say that right now there's a lot ongoing on DC, but I will say that there's a lack on AC microgrid systems, and it's a very exciting area also to work. So we will be very open to collaborate in this area.
Thank you. The other question was a smart meter connected at smart home system. Did you see much noise, and if how it was handled?
Well, the point is that the smart meters that right now we are having, for instance, here in Denmark, are used for the utility to see, basically for billing us, but they can also see power quality problems. Indeed, they can see voltage, if the voltage is going up or down, especially right now that we have a lot of crazy people like me putting solar panels in the roof and electric vehicles connecting to the grid. So you create a lot of imbalance and also voltage up and down, and also even THDs. You can measure THDs. So this is from the utility viewpoint, and there's a lot of work, let's say, to do in the area of big data in order to obtain or extract the needed information to improve the power quality for the grid. But from the user viewpoint, this is not so important. I will say that right now you are able to extract the information from your smart meter. Otherwise, you should contact your utility in order to get it. For instance, here in Denmark, it's possible that you get your own information. And by means of some cards that you can buy from third parties, you could use it also internally to, let's say, optimize the energy efficiency of your home. So I will say that this is something very nice, and it's happening right now. Some companies here in the area of north of Denmark that they are having, let's say, business cases to put those devices in the market.
And the next question is that, is there any study or you are working on using microgrid as a flexible load in context of energy markets and bidding?
Yeah, right now not, but we understand that if the market is enough flexible, we could do it, because, for instance, you may know that here in Denmark we have sometimes that even electricity price becomes negative because we have so many wind power production. You have to imagine that we have around along 1 year we have 60% of the electricity, well, a little bit more than 50% of the electricity coming from the wind. So sometimes we have so much wind that we encourage. This is especially for big loads. Right now it has not been involved microgrids, but I believe that in the future it could also be beneficial for that. So suddenly the microgrid could absorb this electricity when the price, for instance, is negative, not only when it's low. So that could be something really useful here.
Yeah. What do you think about cloud computing, for all this management and coordination in clustered microgrid?
Yes, this is something that we saw that it can be very exciting to have it, especially when you try to have, for instance, digital twins of those multi-microgrid systems to solve, let's say, the objectives, and to go back and give optimum solutions. So I will say that this is a very good tool, and as you mentioned, especially when you have multiple microgrid clusters. So I will say that especially when you have a huge number of microgrids.
Mm-hmm. So next question is that, is there any standard test system for DC microgrid, especially in rural electrification?
It's a good question. Right now, there is not exactly a standard, but there are some, at least in Europe, what we have is IEC standards for, let's say, DC distribution systems below 1000 volt. And I will say that DC microgrid, we could, for rural applications, we could consider that is a DC distribution system below this 1000 volt, and it could be used. They define also power electronics converters, the standardization, and many other things. So I believe that some of these standards could be used.
Mm-hmm. Next, I think 2 questions relate to frequency, and then how frequency is regulated with all power electronics based converters and no rotating machine.
Yeah. Well, in our case, we are using the frequency when, as you say, if you don't have any rotating machine, you can have a number of converters. And if you make these converters working as synchronous generators, finally you are emulating these frequency variations, and this way they can be synchronized each other, as I showed before with the examples of multiple metronomes. So we kind of using the frequency indirectly to emulate that behavior. So what we do is we couple active or reactive power, depending on how is the nature of the line, coupling with the frequency, and that's how it works. But of course, you have to imagine that this is just a convention. So we know that when you go to big power systems with synchronous generators, thanks to this coupling between power and frequency, they can operate in parallel. But if you think on a totally, let's say, separate system, and this system don't have any rotating machine, we could think on other ways of intercommunicating them and to work. So it's not necessary to be like this. It's just that we found the more easy way that can be done, which is just emulating something that in physics exists. And you can find, this is very interesting, many of the different proposals that you can see on how to put in parallel a number of inverters. It's all of them using the Drup concept. If you go to virtual synchronous machines, if you go to the synchronous generator, if you go to the concept of virtual oscillators, all of them, finally, you can demonstrate it mathematically. They are dropping the frequency according to the power. So that's how we get inspired. We are just inspired by physics in that case.
Mm-hmm. Next question is that, can you compare in terms of advantage and disadvantage for hierarchical versus distributed control? I think it's a very broad question though.
Yes. It's a good question. I will say that it changes case by case, but I can give you a little bit. I want to just be very concrete and to give one example from my experience. Right now, in a very recent project, we try to put, again, a number of UPS systems in parallel, right? So once we try to do that, we could restore, let's say, frequency and voltage, especially voltage, because the frequency can change, but in a range very small, thanks to that the frequency is a global variable you can find everywhere, but voltage is not. And the best solution we find for this product, it was to share, let's say, the voltage error between them. So let's say that by using a distributed control was really very efficient, because on that product, we have like a monitoring system, which is connected to some display and something for the user, but it's not fast enough to give back the, let's say, the control commands. So, and in that product, we use CAN bus. So the CAN bus, once you put something in the bus, automatically all the other elements will see this data, and they will get the identification and say, okay, this data is for me, and they will compute it. So I will say that it works very well, very fine when you are thinking on this kind of file buses like CAN bus or many other industrial buses, right? So using distributed control is not so strange as we think. There are many products in the market that they are using. So my experience was, when you have this kind of field buses, is really nice to work on distributed control systems. When you think about wireless, I will tell you, okay, be careful. Be careful, because sometimes you send some message and it's, maybe this message is lost because there's some machine right now starting and they will maybe collapse the system. So sometimes it's a little bit difficult, and you have to think on case by case.
So there are a few more questions. I think we are over time,
Yep.
but we'll go 3 more minutes.
All
so
right.
One question is, you talked about data analytics and, and for power quality, what other applications of data analytics will be good in microgrid?
Sorry, I talk about power quality and what else?
Data analytics.
Yes.
So what other applications of data analytics will be useful in microgrid research?
Sorry, what other?
What other useful research areas, what additional insight we can get other than power quality using that?
Okay, yes. Well, I will say that it's really broad. So if you think that, for instance, to work on resiliency and faults, for instance, what happened when I make a short circuit in my microgrid? What will happen? How I can, let's say, be still operable during this short circuit? How my equipment is able to also go through this short circuit thing, for instance. So you can imagine that all about protections is very important, and also safety for people and so on. So that's a very important field. Mm-hmm. But of course, there are many other fields, like if you look inside the battery systems, We have to think about, for instance, what kind of technologies. Energy storage hybridization, I think it's also very important, because you can see that in many of these microgrid systems, the life of batteries are very critical. So how can we, let's say, hybridize energy storage systems to get a longer, for instance, life for those batteries? If you think to have other kind of elements also, how to integrate them. So I will say that this is so broad that it will change a lot from case to case. So my advice is to try to see which is the field you want to work on. So as I mentioned before, you can have, if you think about that your applications are more on offshore, for instance, off-grid applications in rural areas, this is one case. But if you go and you want to solve, for instance, an electric ferry, this is a total different case. So I will say try to find which is the case you want to solve, because the microgrid is not something tangible. It's a philosophy, right? It's a philosophy that says I try to generate, consume, and store the energy, the water, or whatever the good I want to manage, all the time close each other. That is the main thing. Small is beautiful, no? This is the idea. So behind the word microgrid, you have to be very careful, because then you will find very different applications between them. Even right now, we can see that some, for instance, offshore wind farms or large power plants are also going to microgrid concepts, like trying to have more grid forming converters, because they know that they have to participate also on the frequency and participate, let's say, working as a grid that could be also independent. So right now, a lot of wind farms, also one of the requirement here in Europe and many other places is like, please, can you, for instance, work in Ireland? Can you also perform a black start operation? So that's why I'm saying that it's very important to fix which is the area you want to work in, or which areas are more close to the industry that are connected to your region or to your, let's say, industrial partners, right?
Mm-hmm. So I think last question is that, which is about DC versus AC. So when you have a hybrid microgrid, do you see DC disturbance going to AC side and AC disturbance going to DC side? And do we control both together, or what would be the mitigation technique?
Yeah, that's a very nice question. Because again, you have to see how is this hybrid microgrid system perform. I mean, when you try to generalize these things, it becomes very complex, right? But when you, let's say, go to the real application, then maybe this complexity is not so, such as when you consider, let's say, n number of elements connected to, it's becoming much more concrete. So I will say that first we have to see exactly how is this hybrid microgrid system working, because maybe sometimes if you have to think about a DC bus which is connected by a number of converters, it's not the normal case that all of these converters are connected to the same AC bus, right? So in many cases, what you have is a number of converters that are connected to a common DC bus, and then you can analyze if you have, for instance, constant power loads problem. But it has been also, and this has been discussed a lot, that constant power loads are not so often really a problem, especially when you have losses and you consider non-idealities that exist, right? So, and then you have to see also, so kind of thinking on what is the control system that you are using, because you have to think that if one converter is controlling the DC part, this converter cannot control at the same time the AC part, especially those which are connected to, let's say, between the DC and the AC side. So this means that basically everyone will take care about their side. And there is nothing you can do about it. It will not be a converter that is taking on both at the same time. It's what we call also the interlink converters, right? So the interlink converters will take place more, let's say, on the role of stabilizing one and the other side. But I will say that we can do this basically in a very autonomous way. If the ones who are injecting power to the AC side are having kind of frequency regulation, so let's say that if the frequency is going very high, like we have in photovoltaic systems, as I present today, then the power will inherently go down when this frequency is going up to the collapse. So automatically the system will be regulated, right? And then if you have a DC side, it will happen the same. The DC converters will sense all the time the DC voltage. If they see that the DC is going very high, then automatically they will reduce the power. And then it plays the role of the interlink converters. So in the interlink converters, you can take care of the DC side or on the AC side. And then you have to adjust according to how is the power flow in one or the other direction. So it's a little bit more complex, but also could be a little bit more easy to control in a, let's say, in a very decentralized way.
The last question is that, do you recommend any book on microgrid control?
Book on microgrid control. Right now, I think that Nikos from Greece, Professor Nikos, he have a book, and there is some parts on the control system. But I will say that there are some review papers you could find that are very good. And however, I will say that even there are some books with some chapters, even there are some review papers, I will say that there is a lack of connection with the real applications. So then I will say that it's lacking something that links the manual of the equipment with those controllers. So once you have to use converters that you have to take from the market, then it's difficult to make this link. No? So I will say that, yeah, try to read some reviews, and then you try to read some maybe applications from some manufacturer, and if you make the mix, maybe you will have the right direction. Otherwise, you always are welcome to contact us as well.
Right. So one more question. So
yes.
Between two AC microgrid with the DC interlink, can we transfer the reactive power?
Well, this question, it's a nice question. If you have two AC microgrids and they are connected through a DC link, they can transfer the reactive power if the converter, it's, let's say, big enough to manage the reactive power.
Okay.
Yes, so this, we have to dimension this converter that is in the middle. You know, if this converter is, let's say, busy because it's transferring active power and it don't have any margin to give reactive power, or it's given by the DC link, so we have to dimension maybe a DC link with also, let's say, high capacity, but still the converter have to or dimension it much bigger or to reduce this amount of active power. So finally, it's a matter of design. But the question, let's say that, yes, it is possible, but we have to dimension the converter accordingly.
Mm-hmm. Well, thanks so much. I think there was a lot of interest, and that's why we had so many questions. I did skip through some question, which was very broad.
Thank you.
Yeah.
Thank you for the questions. I think that the questions were even better than the answers.
Well, yeah, thanks so much for doing it in late evening.
Yeah, thank you.
Yeah, thanks.
It was my pleasure. Thank you. Thank you, everyone.
Thanks, bye.
Thank you.